New Deep Dive.
Welcome, curious minds, to the deep dive. Today we're plunging into one of the most, mind-bending concepts in the entire universe. Black holes. They really do seem like an error in the cosmic code, don't they? Something that just completely defies our everyday intuition and pushes the boundaries of what our brains, the ones evolved for conditions right here on Earth, can even start to wrap themselves around. So our mission on this deep dive, using the sources you've shared, is to embark on this fascinating journey. We want to understand what black holes truly are. How do we even first grasp their existence? What incredible phenomena might lie inside them? And how do they keep challenging, the very limits of our cosmic understanding? Okay, so let's unpack this. Where did the very idea of something so strange, so absolute even begin? It's surprising, but the first hints go way back, back to the 18th century, long before Einstein, with an idea called dark stars.
That's right. Back in the 1780s, there was an English clergyman and natural philosopher, John Michell. And working just with Isaac Newton's ideas about gravity, he reasoned something pretty radical for the time. He thought, well, if an object were massive enough, just incredibly dense, its gravity would be so strong that even light couldn't escape its surface. Remember, they knew light had a finite speed then.
Huh. So like a star that's just invisible because its own gravity traps its light.
Exactly. But what's really fascinating here is that while the concept sounds similar, light can't escape, Michell's dark stars were fundamentally different from what we now call black holes. He imagined them as actual physical objects, made of incredibly dense matter. Hypothetical, of course.
Right, not like the modern idea, which is more about space-time itself.
Precisely. Today's black holes, the ones born from Einstein's general theory of relativity, they're understood as features of warped spacetime, the original matter that collapsed to form them. It's thought to be, well, annihilated at the center, gone.
Okay, so that brings us to Einstein. The real intellectual leap, the game changer, was his general theory of relativity. He completely flipped our understanding of gravity. It's not a force pulling things together, but it's the actual curvature, the warping of space-time caused by mass and energy.
Yeah, and the physicist John Wheeler had that famous, really concise summary. Matter and energy tells space-time how to curve, and space-time curvature tells matter and energy how to move.
It's such an elegant idea, a deep connection between the universe's contents and the fabric of reality itself.
It is, and this is where the initial surprise or maybe confusion came in. Black holes were first, you could say, discovered on paper. They just popped out as theoretical solutions to Einstein's equations.
Solutions he didn't ask for.
Kind of, but the funny thing is the initial discoverers, and this includes Einstein himself, they often just dismissed them. They saw them as mathematical quirks, maybe errors in the math, not something that could actually exist out there in the universe.
So Einstein doubted them.
Oh, absolutely. He famously doubted their physical reality for his entire life. He thought nature would find a way to prevent them from actually forming.
Wow. Okay, so if even Einstein wasn't buying it, what pushed the idea forward?
Well, an unexpected breakthrough came from a really unlikely situation during World War I.
Wartime physics.
Yeah. Karl Schwarzschild, a German physicist serving as an artillery officer on the Eastern Front. In his spare time, apparently, he found an exact solution to Einstein's incredibly complex field equations, specifically for the space-time geometry around a perfectly spherical, non-rotating mass, like a simple star or planet.
And what did that solution show?
It showed something really bizarre happening at a specific distance from the center of this mass. A distance we now call the Schwarzschild radius.
How bizarre.
Well, for Earth, this critical radius was tiny, about 9 millimeters, like smaller than a marble. For the Sun, it was about 3 kilometers.
So you'd have to crush the Earth down to the size of a sugar cube, basically.
Pretty much. And at the time, that just seemed completely unphysical. No one knew of any process that could make something that dense. So for decades, it was mostly treated as just a mathematical curiosity. A strange feature of the equations, but probably not real.
Okay, so we have this mathematical oddity. How do we get from there to thinking this could be a real physical process, like something actually happens to make one?
Right. The next big step was modeling stellar collapse. What happens when a really big star runs out of fuel? This was tackled by Robert Oppenheimer. Yes, that Oppenheimer and his student Harold Snyder back in 1939. They published this really groundbreaking paper. It showed that if a sufficiently massive star exhausts its nuclear fuel, its own gravity wins, the core collapses catastrophically, and based on general relativity, it would inevitably form what we now call an event horizon.
The point of no return.
Exactly, the boundary beyond which nothing, not even light, can escape. Their work provided the first theoretical model of how a black hole could actually form from a real physical object.
But weren't their calculations simplified?
Oh, definitely. It was a brilliant conceptual leap, but you have to remember this was 1939. No computers. All calculations were done by hand, on paper. So Oppenheimer and Snyder had to make some pretty big assumptions, like the star collapsing with perfect spherical symmetry, no rotation, no bumps, nothing messy.
Because the real equations were just too hard to solve otherwise.
Exactly. Einstein's equations are notoriously difficult. Solving them for more realistic, messy scenarios was just impossible back then. So idealizations were essential to even get an answer.
It's amazing. And even then, they weren't calling it a black hole, right?
Nope. That iconic name came much later. It was popularized in the 1960s by the physicist John Wheeler. Apparently, he picked it up from a science journalist who used it at a conference, and Wheeler just ran with it because it was so evocative.
And the 60s were a big decade for this field, weren't they?
Absolutely. It's often called the golden era of general relativity. So much progress happened. A huge breakthrough was by Roy Kerr, a physicist from New Zealand. In 1963, he found an exact solution for rotating black holes.
Why was that so important?
Because everything in the universe spins. Stars spin, galaxies spin. A solution for a non-spinning black hole is useful but unrealistic. Kerr's solution described black holes with angular momentum, and it revealed even weirder properties, like the singularity inside not being a point but a ring.
A ring singularity. Wow.
Yeah. And around the same time, observationally, things were heating up too. Jocelyn Bell Burnell discovered pulsars in the late 60s.
Which are spitting neutron stars, right?
Exactly. These incredibly dense remnants of dead stars. Finding them was huge because they showed that matter could be crushed to densities just shy of forming a black hole. It made the idea of complete collapse seem much more plausible.
So the theory and observation were kind of converging.
They were. And then came perhaps the most crucial theoretical step for acceptance. Roger Penrose, using really powerful new mathematical techniques, proved something profound. He showed that the formation of a singularity at that point or region of infinite density where the theory breaks down wasn't just a quirk of those highly idealized, perfectly symmetrical solutions like Oppenheimer's. Penrose proved that singularities were a general, unavoidable consequence of gravitational collapse in Einstein's theory under pretty reasonable conditions.
So it wasn't just a mathematical artifact. The theory demanded them.
Pretty much. That was a turning point. It really helped convince the physics community that black holes weren't just theoretical curiosities, but should actually exist out there.
Is that when the famous bet happened? Between Thorne and Hawking?
Yes. The bet over Cygnus X1, a powerful X-ray source discovered in the 60s. Kip Thorne was convinced it was a black hole orbiting a star. Stephen Hawking, playing devil's advocate perhaps, bet against it. As more evidence mounted for Cygnus X1 being a black hole, Hawking eventually conceded the bet in, I think it was 1990.
And the stakes.
Famously, Hawking had to buy Thorne a one-year subscription to Penthouse magazine. Thorne said Hawking paid up, though maybe a bit reluctantly.
Okay, so the theory is solidifying. People are starting to believe. Now the hunt is on to actually find these things, right? Where did the first hints come from observationally?
Well, some of the earliest, really compelling, though still indirect evidence came from quasars. These were discovered in the late 1960s, early 70s. Quasar stands for quasi-stellar object. They looked like faint stars, but they were incredibly bright and extremely far away, meaning their actual energy output was just colossal.
Brighter than entire galaxies sometimes.
Yes, exactly. And the only explanation that really made sense for that kind of power coming from a relatively small region was a supermassive black hole at the center of a distant galaxy, actively feeding on enormous amounts of gas and dust.
So seeing the effects of their feeding frenzy, basically.
Precisely. The light wasn't from the black hole itself, but from the matter getting superheated as it spiraled in.
Okay, that's distant galaxies. What about closer to home, like in our own Milky Way?
Right. The center of our own galaxy provided even stronger evidence. This took decades of painstaking work. Astronomers, using powerful telescopes, especially in infrared light, to pierce through all the dust, started tracking the orbits of individual stars very close to the galactic center.
These are the S stars I've read about.
That's them, like the star S2. They observed these stars whipping around an unseen central point at incredible speeds. By carefully mapping their orbits over many years, they could calculate the mass of whatever they were orbiting.
And the mass was huge.
Immense, over 4 million times the mass of our sun, all crammed into a region smaller than our solar system.
And crucially, nothing visible there.
Nothing visible that could possibly account for that much mass and that intense gravitational pull. The inescapable conclusion was a supermassive black hole, now known as Sagittarius A, lurking right at the heart of the Milky Way.
That's incredible, seeing stars dance around invisibility.
It really is. It was powerful, compelling evidence. Even though you weren't seeing the black hole directly, the gravitational effects were undeniable.
So we had the feeding frenzy of quasars, the invisible gravitational anchor in our galaxy. But then came something even more direct, right? Actually hearing them.
Or, more accurately, detecting the ripples they make in space-time itself. Gravitational waves. This was the game changer in 2015.
LIGO, the Laser Interferometer Gravitational Wave Observatory.
Exactly. LIGO made the first ever direct detection of gravitational waves. And what produced those waves?
Two black holes merging.
Bingo. Two stellar mass black holes, maybe 30 times the mass of the sun each, spiraling into each other and merging into one larger black hole billions of light years away. This confirmed another of Einstein's predictions, gravitational waves themselves, something he also initially doubted. And it was the first time we directly detected black holes interacting.
And the energy release was just insane, right?
Unbelievable. In that first event, something like 3 entire solar masses were converted directly into pure gravitational wave energy in just a fraction of a second. EMC squared on a cosmic scale.
Wow. And since then, these detections have become almost routine.
Almost, yeah. When the detectors like LIGO and Virgo are online, they're now picking up black hole mergers or neutron star mergers, sometimes every few days. It's opened up a completely new way to see the universe gravitational wave astronomy.
And there's more, right? The lower frequency waves.
Yes. Using something called pulsar timing arrays, or PTAs. This involves monitoring dozens of incredibly precise pulsars scattered across the galaxy. By looking for tiny, correlated changes in the arrival times of their pulses, scientists are detecting a background hum of much lower frequency gravitational waves.
From what? Even bigger black holes.
That's the leading theory, likely from pairs of supermassive black holes orbiting each other very slowly in the centers of merging galaxies, long before they finally merge completely. It's like hearing the slow dance of cosmic titans.
The precision needed for all this is just staggering.
It truly is. We're talking about LIGO measuring distortions in space-time, stretches and squeezes that are thousands of times smaller than the diameter of a proton, over kilometers-long detector arms. It's one of the most sensitive measurements humans have ever made.
Okay, theory, indirect evidence, gravitational waves. But the Holy Grail was always going to be an actual picture, wasn't it? Even if it's not a picture of the black hole itself.
Absolutely. And that brings us to the Event Horizon Telescope, the EHT. This wasn't just one telescope, but a global network of radio telescopes.
Spread across the whole planet.
Pretty much, from Hawaii to Spain, Chile to the South Pole. By combining their data using a technique called very long baseline interferometry, they effectively created a virtual telescope the size of the Earth.
To get the resolution needed to see something so small and so far away.
Exactly. And in 2019, they unveiled that iconic first image. It was the supermassive black hole at the center of the galaxy Messier 87, or M87.
Which is a monster, right? Billions of solar masses.
Yeah, about 6.5 billion times the mass of the sun. And the image. It wasn't the black hole itself, because that's impossible to see.
It was the shadow.
It was its silhouette, its shadow, cast against the backdrop of the superheated gas swirling around it in the accretion disk. A dark central region surrounded by a bright ring of light.
And it looked just like the theories predicted.
Remarkably so. Especially Kerr's solution for a rotating black hole. That image was a stunning confirmation of general relativity in the most extreme environment imaginable.
And they imaged our own galaxy's black hole too, Sagittarius A.
They did a few years later. That was actually much harder, technically. Even though SGR-A is closer, it's much smaller than M87's, and the gas around it is swirling much faster, changing on timescales of minutes rather than days. So it was like trying to take a clear picture of a flickering candle compared to M87's steady bonfire.
And the data. Didn't they have to fly hard drives back from Antarctica?
That's right. The amount of data collected by the EHT network was so enormous petabytes that it couldn't be transferred over the internet, especially from remote sites like the South Pole Telescope. So they literally had to physically fly crates of hard drives back to central processing centers to correlate all the signals. Old school meets high tech.
That's amazing. What a logistical feat on top of the scientific one.
Absolutely. And what's so cool about those images is how clearly you see the effects of extreme gravitational lensing. Light from behind the black hole gets bent around it, making the ring look brighter on one side, the side rotating towards us, and creating these distorted views. It's like seeing gravity itself bend light right before your eyes.
All right, let's take the plunge, hypothetically speaking. Imagine you're an astronaut falling into a black hole. What's the experience like? I always hear about spaghettification.
Ah, yes, spaghettification. It's a wonderfully descriptive term for a truly unpleasant fate. It happens because of tidal forces. The gravity pulling on your feet, assuming you're falling feet first, is significantly stronger than the gravity pulling on your head because your feet are closer to the center.
So you get stretched.
Stretched vertically and squeezed horizontally, like spaghetti. For a smaller, stellar mass black hole, these tidal forces become lethal before you even reach the event horizon. You'd be torn apart.
Okay, note to self. Avoid small black holes. What about the big ones, like M87s?
That's the counterintuitive part. For a supermassive black hole, billions of solar masses, the event horizon is much, much farther out from the singularity. The curvature of space-time at the horizon is actually quite gentle. So the tidal forces at the horizon are relatively weak. An astronaut falling into M87's black hole could, in theory, cross the event horizon without immediately feeling anything amiss. Spaghettification would still happen, but much deeper inside, closer to the singularity.
So you could cross the point of no return without even realizing it initially.
Initially, yes. Although other weird effects would start becoming apparent, like frame dragging, especially if it's a rotating black hole, which they almost certainly are.
Frame dragging, what's that?
It's also called the lens thirring effect. A rotating black hole literally drags space-time around with it, like twisting a vortex in honey. As you fall in, space-time itself forces you to start orbiting the black hole in the direction of its spin. You can't just fall straight in anymore. This is part of why accretion disks form and spiral inwards. Space-time itself is swirling.
Okay, so you cross the horizon, maybe feeling okay for a bit, but space-time is swirling around you. What would you actually see?
Visually, things get incredibly strange. Remember, the event horizon isn't a physical wall. It's just a boundary in space-time. You wouldn't bump into anything. But the way light behaves gets warped dramatically. Due to extreme gravitational lensing and relativistic effects, the light from the universe behind you gets bent around and appears to come from in front of you.
Wait, so the stars behind me would appear in front of me?
Yes, and they'd be intensely blue-shifted because you're falling towards that light source effectively. The entire visible universe would eventually seem to compress into a smaller and smaller, brighter and bluer circle directly ahead of you.
What about looking back towards the universe you left?
Looking back becomes impossible. All light paths, even those starting outwards, are curved so strongly inwards that they inevitably lead towards the singularity. There's literally no path for light from behind you at the horizon to reach your eyes anymore. You're trapped.
Okay, so visually distorted, forced to spiral in. What's the ultimate destination? The singularity. What is that?
That's the million-dollar question, in a way. Mathematically, in classical general relativity, the singularity is a point for a non-rotating black hole, or a ring for a rotating one, where the density of matter and the curvature of space-time become infinite.
Infinite. That sounds like the math is just breaking.
That's exactly what it means. It signals the breakdown of general relativity. Our current theory can't describe what happens at the singularity. It's telling us we need a better theory, likely one that incorporates quantum mechanics, a theory of quantum gravity.
Well, what happens to the stuff that fell in? The original star or anything else?
According to GR, any matter that falls in is crushed out of existence at the singularity. Black holes are technically vacuum solutions, meaning apart from the singularity, there's no matter inside, only warped space-time. The matter gets annihilated.
Just gone.
According to the classical theory, yes. Penrose and Hawking's singularity theorems prove mathematically that, within GR, these points of breakdown are unavoidable once an event horizon forms. For rotating black holes, the picture might be even more complex, potentially involving chaotic, destructive oscillations near the ring singularity, something called the BKL singularity, but the endpoint is still infinite density and the breakdown of physics as we know it.
Are there any alternatives? Ideas that avoid this infinite point?
There are speculative ideas, things like gravistars, where the collapse halts just before forming a singularity, creating a kind of exotic shell surrounding a region of vacuum energy. Or ideas from loop quantum gravity that might replace the singularity with a quantum bounce. But these are still very much theoretical and lack observational evidence. For now, GR points firmly towards a singularity.
Okay, so inside seems like a place where our physics breaks.
Yeah.
But there's another huge twist, right? Something involving quantum mechanics outside the black hole. They're not completely black.
Exactly. This was Stephen Hawking's monumental discovery in the 1970s, Hawking radiation. He showed that when you combine general relativity with quantum field theory near the event horizon, black holes aren't perfectly black. They should actually emit a faint glow of thermal radiation.
They radiate, so they lose energy.
Yes, they slowly lose mass and energy through this radiation, meaning they actually evaporate over incredibly long timescales.
How long?
For a solely mass black hole, we're talking vastly longer than the current age of the universe, like 10 to the power of 67 years, an unimaginable time. But for much smaller, hypothetical black holes, the evaporation could be much faster.
And smaller ones are hotter.
Counterintuitively, yes. The smaller the black hole, the higher its temperature and the faster it radiates and evaporates. Tiny black holes would explode in a flash of radiation.
How does this radiation even happen? I've heard the analogy about virtual particles.
Right, the virtual particle pair analogy is common. One falls in, the other escapes, looking like radiation. It captures some of the idea, but it's a simplification. A more accurate picture involves the intense gravitational field near the horizon interacting with the quantum vacuum, the sort of frothing sea of virtual particles that exists everywhere in space-time according to quantum field theory. The strong gravity basically excites these quantum fields, converting virtual fluctuations into real particles that can then escape out to infinity. It's a subtle quantum effect happening right at the edge of space-time.
Wow. So quantum mechanics makes black holes leak. What does that do to our understanding of information?
Now you've hit on one of the deepest mysteries in modern physics, the black hole information paradox.
Okay, what's the paradox?
It starts with something called the no-hair theorem. This theorem in classical GR says that a black hole, once it settles down, is incredibly simple. It's defined only by three properties: its mass, its electric charge, usually assumed to be zero or negligible, and its angular momentum, spin.
No hair, meaning no other features.
Exactly. It doesn't matter if you made the black hole out of collapsed stars or Encyclopedia Britannicas or teacups. Once it forms, all that complex information about what fell in seems to be lost, hidden behind the event horizon. The black hole only remembers mass, charge, and spin.
Okay, so information seems lost. Why is that a paradox?
Because one of the fundamental principles of quantum mechanics is that information is never truly lost. It might get scrambled and hard to read, but it should always be preserved in principle. So, if a black hole forms, swallows a bunch of information, like the contents of those encyclopedias, and then completely evaporates away via Hawking radiation, which Hawking initially calculated to be perfectly thermal and random, where did the information go?
It seems to have just vanished, violating quantum mechanics.
That's the paradox. It pits general relativity, which says information falls in and hits the singularity, against quantum mechanics, which says information must be conserved. Resolving this is a huge driver in the search for a theory of quantum gravity.
Are there proposed solutions?
Many. One fascinating idea is the holographic principle, which suggests maybe the information isn't lost inside, but is somehow encoded on the 2D surface of the event horizon, like a hologram. Stephen Hawking himself famously changed his mind later in his career. He came to believe that information isn't lost, but is subtly encoded in the correlations within the outgoing Hawking radiation, although precisely how is still debated fiercely.
It feels like black holes are forcing us to rethink everything.
They really are. They're theoretical laboratories for the most extreme physics, and they lead to even wilder speculations.
Like white holes.
Exactly. Mathematically, the equations of GR allow for solutions that look like time-reversed black holes, objects that nothing can fall into but from which matter and energy constantly stream out.
Do we think they exist?
Probably not. While mathematically possible, there's no known physical process that could form one. They mostly remain a theoretical curiosity, perhaps relevant in scenarios involving wormholes.
Ah, wormholes, the classic sci-fi shortcut through space-time. Are they related to black holes?
Theoretically, yes. The simplest type of wormhole, the Einstein-Rosen bridge, actually appeared in the mathematics of the Schwarzschild black hole solution. It looks like a tunnel connecting two different points in spacetime, or maybe even two different universes.
Could you travel through one?
Probably not. These simple wormholes are thought to be incredibly unstable. They'd likely pinch off and collapse faster than even light could cross them. To keep one open might require exotic matter with negative energy density, something we've never observed.
And time travel.
Also highly speculative, but theoretically, if you could create a stable wormhole and then, say, accelerate one end to near light speed and bring it back, the time dilation effects might turn it into a time machine allowing travel to the past. But again, this relies on seemingly impossible physics.
It doesn't stop there, does it? Some people propose our whole universe is inside a black hole.
That's a more speculative idea called black hole cosmology. The thought is that the conditions inside a very large black hole might, under certain theories extending GR, resemble the conditions of an expanding universe like ours. Maybe our Big Bang was the result of matter collapsing into a black hole in some parent universe?
A universe within a universe.
It ties into ideas like the Big Bounce, where our universe might collapse and reemerge, potentially through a black hole-like state, or theories like Einstein-Cartan theory that replace singularities with wormholes to new universes. Highly speculative, but mind-bending stuff.
Okay, let's bring it back to Earth for a second. What about the fear, sometimes you hear it, about particle accelerators like the LHC at CERN, accidentally creating tiny black holes that could swallow the Earth?
Right, that concern pops up occasionally. Theoretically, if there are extra spatial dimensions beyond our usual three, it might be possible to create microscopic black holes at the high energies achieved in colliders like the LHC, or even from extremely high-energy cosmic rays hitting our atmosphere.
Is it a danger?
Overwhelmingly, the scientific consensus is no, absolutely not. There are two main reasons. First, we haven't seen any evidence of them being produced. Second, and more importantly, remember Hawking radiation.
Ah, the evaporation.
Exactly. These hypothetical micro-black holes would be incredibly tiny, far smaller than a proton. According to Hawking's theory, this means they would be incredibly hot and would evaporate almost instantaneously in fractions of a second, like 1027 seconds in a tiny puff of standard model particles.
So they'd disappear before they could possibly grow or swallow anything.
Precisely. They wouldn't have time to accrete any matter at all. Plus, nature has been doing this experiment for billions of years. Earth's atmosphere is constantly being bombarded by cosmic rays with energies far exceeding what the LHC can produce. If dangerous micro-black holes could be formed, we'd have seen the effects long ago. Earth is still here, so we're safe.
That's reassuring. Okay, one last area of extreme space-time weirdness, cosmic strings.
Another fascinating theoretical possibility. Cosmic strings are hypothesized to be incredibly thin, possibly infinitely thin, one-dimensional defects in the fabric of space-time itself. Think of them like cracks or topological defects left over from phase transitions in the very early universe.
Like cosmic threads stretching across the universe.
Kind of, yeah, and they would have immense mass per unit length, meaning they'd warp space-time significantly. There's even speculation that two parallel cosmic strings moving past each other at high speeds could warp spacetime so much it might create closed time-like curves, effectively a time machine. Again, highly speculative.
Is there any evidence for them?
Potentially. Remember those low-frequency gravitational waves being detected by pulsar timing arrays? While merging supermassive black holes are the leading candidate, some researchers suggest that vibrating loops of cosmic strings could also produce such a gravitational wave background.
So it's still an open question.
Very much so. The upcoming LISA space-based gravitational wave observatory, planned for launch around 2035, will be much more sensitive to these lower frequencies and might give us definitive answers about both supermassive black hole binaries and maybe even cosmic strings.
Amazing. From black holes to cosmic strings, wormholes, maybe even other universes. It seems like the edges of our understanding are full of weird and wonderful possibilities.
That's what makes this field so exciting. We're constantly pushing the boundaries of what we know about gravity, space-time, and the quantum world. #tag outro.
So we've taken quite a journey today. From John Mitchell's early dark stars, based on Newtonian ideas, through Einstein's revolution and the initial dismissal of black holes as mere math,
to the theoretical breakthroughs of Oppenheimer, Penrose, and Kerr, the naming, the Golden Age, and finally the observational triumphs, quasars, Sagittarius A, the incredible detections of gravitational waves.
and culminating in actually seeing the shadow of a black hole with the Event Horizon Telescope. We've peered, hypothetically, inside, encountering spaghettification, frame dragging, and the ultimate mystery of the singularity.
And we've touched on the quantum weirdness, Hawking radiation, the information paradox, and the even wilder speculations about white holes, wormholes, and the very nature of our universe.
So black holes truly remain one of the most profound enigmas. That point where our best theory, general relativity, just breaks down at the singularity. It's like a giant signpost, isn't it?
It really is. It's pointing towards a deeper level of reality, a theory of quantum gravity we haven't discovered yet, one that can unify these seemingly disparate realms of physics and explain these extremes.
So as we wrap up this deep dive, here's something for you to ponder. What truly lies beyond the event horizon? Are singularities really the end of the line? Points of infinite destruction?
Or are they perhaps gateways, not necessarily in a sci-fi sense, but gateways to new physics, pointing the way to a more complete understanding of the cosmos?
The quest continues. And trying to unravel the secrets of black holes will undoubtedly keep redefining our understanding of space, time, and reality itself.
Subscribe to New Deep Dive.